Hello and welcome to this Unisensor microsensor lecture. My name is Lars Hauer Larsen and I am CSO here at Unisense and responsible for production and development of Unisense microsensors. In this presentation I will give you an introduction to how our hydrogen microsensors are designed and working, which hopefully will familiarize you with them and help you applying them correctly. The Unisense hydrogen microsensor is of the amperemetric microsensor type, also known as Clark type sensors, and a detailed lecture about the working principles for these sensors is available on our website. This lecture will cover the following topics: chip design and detecting principles, the specifications, something about customizations, and at last something about how to troubleshoot the hydrogen microsensor. Details and general theory about Unisense amperemetric microsensors are covered in the lecture about Unisense amperemetric microsensors, but I will here briefly describe the chip design and working principle for the hydrogen microsensors. The outer tapered glass casing is equipped with a silicon tip membrane. The function of the membrane is to make a barrier between the electrochemistry inside the microsensor and the sample. The membrane is permeable to hydrogen. If hydrogen is present, it diffuses through the membrane to the working electrode. The working electrode surface is a positively polarized platinum electrode, which catalyzes oxidation of hydrogen. The electrons are delivered to the reference electrode, where a dissolved substance in the electrolyte is reduced. We do not give detailed information about the electrolyte composition and electrochemical reactions because it is a proprietary recipe which is not protected by patents. The reference is placed 10 to 15 centimeters away from the working electrode, but for sake of illustrating the principles, it is included in the schematic drawing of the chip. The current generated is proportional to the concentration of hydrogen outside the tip membrane, and as the current is very small in the picoamp range, a high quality amperemeter is necessary for amplifying such tiny current. The electrolyte solution ensures electrical connection between the electrodes and ensures charge balance. I will now turn to the actual performance and specs of the hydrogen sensors and give some comments to them. Recall that these specs are only guaranteed with use of a Unisense meter. The limit of detection is stated to be 0.3 micromolar dissolved hydrogen. However, the detection limit is strongly influenced by the application in question. By producing the hydrogen sensors with a wider tip membrane, the sensors can be made more sensitive with a detection limit down to 50 nanomolar. The detection limit will, however, increase the sensitivity to steering. The tip size ranges from 10 to 500 micrometers. We produce them in standard models with 10, 25, 50, 100, 200 and 500 micrometers. Naturally, the smaller the tip is, the more fragile it will be. Larger sensors are made with thick glass walls, making them quite robust for profiling in matrices like sediments. Consult our guide for tip size selection for more information. We can custom-made the tip design regarding slenderness and modify the body dimensions if requested. The response time is a function of the hydrogen diffusion path length into the working electrode and chosen to obtain the best compromise between sensitivity, response time, and steering sensitivity. Hydrogen sensors can be made very fast responding, down to less than 1 second. Our standard sensors respond linearly to dissolved hydrogen in concentrations from 0 to supersaturated solutions, as well as in gas samples from 0 hydrogen to pure hydrogen gas. Our low-range versions are made for measurements between 0 and approximately 240 micromolar, which corresponds to an equilibrium with 30% hydrogen atmosphere. The spatial resolution equals the tip diameter. This is just a rule of thumb because it cannot easily be validated. The sensor will sample hydrogen from a very minute diffusion sphere at the membrane/sample interface, but when profiling in biologically active matrices, physical disturbance should also be considered, which increases with tip size. The sensitivity to steering is for standard sensors less than 2%, but significantly higher for low-range sensors. For low-range sensors, which can detect hydrogen in the nanomolar range, the sensitivity to steering could be up to 5%. The sensitivity to steering is defined as the difference between the signal in stirred and stagnant sample with the same hydrogen concentration. This is exemplified here, where a sensor is measuring in a continuously mixed sample. When the steering is stopped, the signal decreases about 2%, which is typical for a standard range hydrogen sensor. And when the steering is reactivated, the signal is back to the original level. The lifetime is expected to be long, more than 12 months, if not physically damaged. The loss of working electrode efficiency is the main factor which causes drift. The working electrode surface layer is carefully manufactured to ensure best possible stability, but as it is a handmade process, the drift vary among hydrogen sensors. Typically, a hydrogen sensor is quite stable, however, with a drift less than 10% per month. Physical impact to the sensor can, besides destroying the sensor, change the sensitivity and thereby the calibration curve of a hydrogen sensor. The working electrode connects to the amperemeter via a thin, flexible, glass-covered platinum wire. Physical impact, which shocks the internal components, can induce a displacement of the working electrode position relative to the membrane, thereby changing the sensitivity. Typically, such impact will induce a sudden signal peak, followed by a stabilization time. But the sensitivity might not return to the original sensitivity caused by a displacement of the working electrode position. The hydrogen sensors stand up to 5 times atmospheric pressure without being pressure compensated. However, like other Unisense microsensors and electrodes, we can pressure compensate the inner parts of the sensor, so they do withstand full oceanic pressure. When pressure compensated, they are tested to be able to withstand 600 bars. In the web lecture about amperemetric microsensors, the temperature influence is discussed in details. And it is explained why temperature compensation is difficult for amperemetric microsensors. The temperature interference is about 2% per degree. For sensors used with the new UniAmp portfolio, signal is temperature compensated within a plus/minus 3 degrees Celsius interval. We therefore recommend calibrating hydrogen sensors and measure at the same or almost the same temperature. The sensors can be used from minus 10 to 60 degrees Celsius. At higher temperatures, the baseline and noise level increase and compromise the sensitivity. I will not in this presentation go into details with all the adaptations and modifications we do to the hydrogen sensors. This is covered in the quick guide, but I will at this point describe how a needle-embedded sensor is made. We make needle-embedded versions of the hydrogen sensors in order to give some protection to the sensor tip from being damaged. We make them in 2 different versions, H2N and H2NP. The latter is made for piercing membranes. Both types can be made in low-range versions. This is a schematic drawing of the tip of hydrogen needle sensors and hydrogen piercing needle sensors. The needle protects to some extent the glass, but the sensor tip is still fully exposed to the sample solution. The needle and the glass part of the sensor is glued together inside the needle, so no sample liquid will intrude into the needle. This would otherwise cause a huge carryover effect. I now turn to troubleshooting hydrogen microsensors, which do not exhibit normal performance. Naturally, small glass tip sensors are fragile, and the tip might break if it hits something hard. This is a photo of an intact hydrogen 10 micrometer sensor, and to the right a photo of the same sensor is shown, but now with a broken tip. It is seen how the working electrode is exposed because the glass tip is missing. A broken sensor will in water give a very high signal, typically out of range, as the working electrode is now directly exposed. So if the tip breaks during measurements, a sharp signal rise will occur to the out of range level. It is not possible to repair a broken sensor. If the sensor tip gets biofouled or covered with sticky polymers, it might measure incorrectly. The sensor tip tolerates almost all possible cleaning substances like alcohols, acids, detergents, proteinaceous solution, etc. So it is recommended to insert the sensor in different cleaning solutions to see if this solves the problem as the first attempt to remove the fouling. If chemical cleaning does not remove the fouling and restore normal performance of the sensor, a physical cleaning is the only solution. For 150 and larger sensors, it is safe to wipe the tip with a piece of soft, wetted fabric or paper. If you hold the sensor so the tip points away from you, the wipe direction must always be the direction the tip points, never against the tip, which will impose a risk of tip damage. For 2010 and 25 hydrogen sensors, physical wiping might break the tip. For physical cleaning of these fragile sensors, we recommend that you hook the sensor up in a microprofiling system and gently insert the sensor in a soft matrix, which gives some shear force on the fouling material, and remove it. The best material we know of to do this is Oasis flour foam. It should be wetted before inserting the sensor. These curves illustrate a normal start-up behavior of a hydrogen microsensor when connected to a Unisense amplifier and polarized. The signal is high and downward drifting right after polarization due to unspecific reactions on the working electrode. The hydrogen sensor quickly stabilizes after connecting it to the amplifier and are ready for calibration after a few minutes of polarization. If there is not such an initial peak signal, but instead the signal does not rise much from zero when connecting it to the amplifier, it might be due to a gas bubble stuck in the tip, which disconnects the working electrode from the reference. There must be a gas/air phase in the electrolyte cavity in order to make room for temperature-induced expansion of the electrolyte. And if the sensor package is turned upside down during shipment, a gas bubble can be trapped in the tip. Such air bubble can be removed by shaking the sensor like demonstrated here. The bubble will become loose and rise to the top of the electrolyte cavity, and connection will be restored. In rare cases, a gas phase can evolve in the tip at the working electrode position, and such gas cannot be removed by shaking. So if there is no signal from the sensor, this could potentially be the explanation. Such gas phase can easily be removed by inserting the tip into degassed water, which will drag the gas out of the tip through the membrane. Fill water into a glass bottle and boil the water. This drags gases out of the water. Let the water cool to room temperature or below without shaking the bottle or mixing the water. Place the sensor tip into the water for some hours. The gas phase will be removed by this procedure. If a sensor experiences a physical impact, like a drop on the table, the working electrode could be displaced. If the displacement results in a working electrode retraction from the silicon membrane, the signal will be slow and sensitivity low. The sensor will still work, but has lost its original performance. It is unfortunately not possible to restore original performance. A physical impact like a drop could also damage the glass insulation of the platinum wire connecting the working electrode. This will typically result in an elevated and noisy baseline signal due to exposure of polarized platinum to the electrolyte. Chemical reactions taking place on the exposed platinum surface will create a current which will overlay the working electrode generated current. The size of the baseline increase will depend on the degree of damage to the platinum wire insulation. Such damage cannot be repaired. Thank you for watching this Unisense microsensor lecture. I hope you enjoyed it. If you have any questions, you are more than welcome to contact us at sales@unisense.com.